Welcome to this explainer. Okay, let's dive right in. When you look at the periodic table of elements today, it feels like this perfectly complete map of the universe's building blocks, right? Like everything is just neatly sorted. But for a really long time, it wasn't like that at all. It was a map full of glaring empty spaces. So today, we're going to explore the fascinating, honestly almost magical mystery of those empty spaces in the early periodic table, and how scientists literally had to invent brand new matter just to fill them in. So, back in 1869, this brilliant Russian chemist, Dmitry Mendeleev, organizes all the known elements into his now famous periodic table based on their properties. And he notices these distinct patterns, sure, but he also notices gaps, blank spaces. But he was so confident in his system that he boldly predicted the existence of elements that absolutely had to fit into those gaps. He even gave them these temporary names using Sanskrit prefixes. Decades pass, though, and scientists are scouring the globe, digging through mines, but they just can't find some of these predicted elements anywhere on Earth. Which really begs the question, why would the universe leave these puzzle pieces blank?
Well, the answer is that these missing pieces are what we call synthetic elements. Basically, these are chemical elements that just do not occur naturally on Earth, and they actually have to be created by human manipulation of fundamental particles. You see, Mendeleev wasn't wrong. It's just that nature couldn't give us these pieces. Or actually, scratch that. Nature just couldn't preserve them for us. So human ingenuity had to step up and forge what the Earth had lost.
Section 1. The missing building blocks. Let's look at one of the most famous gaps on Mendeleev's table, element 43. Scientists were desperately searching for this thing in the 1920s. Mendeleev originally called it ecomanganese because it sat right below manganese on his table. You had this renowned German husband and wife team, Walter and Ida Noddick, who analyzed ores from over 100 different mines. And they actually found element 75, rhenium, while doing this. But despite sifting through literally hundreds of kilograms of material, element 43 completely ghosted them. It was nowhere to be found. And the relentless math of radioactive decay explains exactly why the Noddacks and, well, everyone else kept coming up empty-handed. Let's walk through this timeline. Element 43 is incredibly unstable, like zero stable isotopes. Its most stable form has a half-life of 4.2 million years. Now, 4.2 million years sounds like a long time, right? But let's put that into perspective. Imagine the entire mass of the Earth was made of pure element 43 when the planet formed 4.6 billion years ago. After 344 million years of half-lives ticking away, you'd only have 1 single kilogram left on the entire planet. Fast forward to 529 million years, you have less than 1 trillion atoms. And by 697 million years, you are down to 1 single atom. So by the time humans evolved and actually started looking for it, element 43 had been completely erased from nature for billions of years. Section 2. Forging element 43. So, since we couldn't just dig it out of the dirt, we had to figure out how to build it from scratch, which finally happened in 1937. The big breakthrough came from this incredibly ingenious step-by-step process by Emilio Segre and Carlo Perrier over in Italy. Now, Segre had recently visited Ernest Lawrence in Berkeley, California. Lawrence had invented the cyclotron, this really early particle accelerator. And he gave Segre a highly radioactive strip of molybdenum that had just been sitting inside the cyclotron, getting bombarded by deuterons. So Segre takes this back to Italy, and he and Perrier get right to work. First, they react the strip with boiling ammonia to strip away the impurities. But the remaining radioactive atoms were just way too minuscule to ice away on their own. So they used a super clever trick pioneered by Marie Curie decades earlier: carrier elements. By adding stable elements like rhenium into the solution, the radioactive atoms basically hitched a ride. They bound to them and could be extracted. After systematically testing and eliminating every known element, they proved that the leftover radioactivity was something totally new. They had actually synthesized element 43. They later named it technetium, which comes from the Greek word for artificial. Section 3. The Seaborg era. Synthesizing technetium proved that building brand new matter was absolutely possible. And honestly, no one rode that wave quite like the legendary American chemist Glenn T. Seaborg. Seaborg was this prolific element hunter with a resume that is frankly staggering. He completely reshaped how we understand the atomic world. He co-discovered 10 new elements that literally expanded the known periodic table by 10%. That includes plutonium, and even an element named after him while he was still alive, Seaborgium. During World War II, he was a section head in the top-secret Manhattan Project. But maybe his absolute greatest triumph was daring to challenge established scientific dogma. He proposed this major realignment of the periodic table to make room for these new heavy elements. His senior colleagues literally warned him that pushing such a radical idea would ruin his scientific reputation. But guess what? He was right, and it won him the 1951 Nobel Prize in Chemistry when he was just 39 years old. Section 4. Beyond uranium. Let's look at a really critical distinction that Seaborg's bold realignment helped clear up. It actually changed the entire geography of the periodic table. You can basically divide the atomic world into two totally distinct realms now. On the left side, you have the elements that nature provides for us for free. That goes from hydrogen at atomic number 1 all the way up to uranium at atomic number 92. But once you cross that line, you enter the realm of transuranium elements, atomic numbers 93 and higher. Every single element past uranium is completely radioactively unstable and has to be artificially created in a lab. So Seaborg and his peers weren't just finding missing puzzle pieces, they were literally building an entirely new wing onto the periodic table.
And this new wing expanded at just a breathless pace in the mid-20th century. Look at this timeline. In 1940, neptunium, element 93, is created. That exact same year, plutonium is discovered. Now, because of plutonium's potential to fuel a devastating atomic bomb, Seaborg's team kept that discovery a heavily guarded military secret for the entire duration of World War II. By 1944, they synthesized americium, element 95. And this march just continued for decades, eventually reaching seaborgium, element 106, in 1974.
Section 5. Everyday artificial elements. Okay, so here's the crucial question. Why does forging these microscopic, super unstable elements actually matter to you and me? Well, I want to let this staggering number really sink in for a second. 40 million. That is the number of medical procedures performed globally every single year using technetium 99M. Let's break down how these artificial elements went straight from the cyclotron into everyday technologies that literally save our lives. Remember that missing puzzle piece, technetium? Well, a specific isotope of it, technetium 99M, is absolutely the workhorse of modern medical imaging today. It allows doctors to see inside the human body to diagnose cancers and monitor blood flow. Then you've got americium. Honestly, you probably have an artificial element in your house right now, because americium is a critical component in household smoke detectors, just standing guard while you sleep. And plutonium? An isotope of plutonium provides the major, long-lasting thermal energy source required to power our probes for deep space exploration. Think about that. We are literally using artificial elements to reach the stars.
And this brings up such a powerful insight from Glenn T. Seaborg himself. He noted that with basic research, the kind where there's no immediate practical application, you don't even know what you'll miss by cutting it, because there's just no way to know what discoveries it will spawn. When scientists first started blasting molybdenum strips with deuterons, they weren't trying to invent modern cancer diagnostics. They were just passionately, intensely curious about how the universe worked. If we neglect basic research, we're basically slamming the door on discoveries that we can't even imagine yet. Section 6. The super-heavy future. So, we've filled in the gaps, and we've conquered the transuranium elements. But where is the frontier of chemistry today? Well, we have to look out at the very edge of the periodic table, where scientists are hunting for what they call super-heavy elements. The ultimate challenge for scientists right now lies with these super-heavy elements, anything with an atomic number of 104 or higher. They are incredibly massive, and because they're so big, they are violently unstable. Most of them decay out of existence in just fractions of a second, sometimes milliseconds. But physicists are dreaming of reaching this theoretical region on the periodic table known as the island of stability. It's this hypothesized sweet spot where super-heavy elements might just have the perfect magic ratio of protons and neutrons, which could allow them to exist stably for days, years, or maybe even centuries. If we can ever reach this island, it could unlock entirely new classes of materials with chemical properties we literally can't even fathom right now. So I want to leave you with this provocative thought to chew on. Does the periodic table have a final, absolute end? Or is our map still incomplete? Nature gave us the first 92 building blocks, sure, but human curiosity and sheer ingenuity have proven that we are definitely not limited by what we can just find in the dirt. We might just be beginning our journey toward that island of stability. Thank you so much for joining me on this explainer. And remember, always stay curious about the ongoing, absolutely magical quest to build new matter.